Good. So, gentlemen, ladies, other assorted chemists. First thing, uh, I got to thinking, honestly, Keaton's question yesterday was bothering me a bunch. Thanks, Keaton. I lost sleep. Now, because his logic was sound, and yet the answer that we were getting was not quite the same. And Keaton's basic observation was this: if the density of mercury is 13.6 times the density of water, then a cup full of mercury should weigh 13.6 times whatever that same cup full of water is. Okay? So, or in other words, if we had a pint, that's 16 ounces, right? So it should weigh a pound, and that means that a pint should weigh 13.6 pounds, right? Because 1 times 13.6, 13.6. But when we did the problem, we were getting a shade over 14. Okay? So it was close, but it wasn't there. And then Keaton's observation was maybe it's a rounding thing. And indeed, it is a rounding thing. So I looked it up, and I unfortunately gave you a missed piece of information. I hang in my head in shame.
I can't believe you done.
Because Pa Pernichek told me wrong. He done did me wrong.
Is a pint of
The
water
old saying
like
is a pint is a pound the world around.
It's like 1 point.
It's not a pound. It's 1.043. So if you take 1.043 times 13.6, you get just the shade over 14, but the exact number is 1.043 times 13.6 is 14.1848 pounds, which was almost exactly what we were getting.
Like
Does that mean the world
1.19.
isn't round?
Yes, you're right, it's not. The technical name for the shape of the planet Earth is an oblate spheroid. It's not perfectly spherical.
I guess I'm an oblate sphere.
Now-
We shouldn't body shape.
Now, basically it means this. If you've ever seen movies where they're like making the hand-tossed pizza, they're doing the whole spin it while you toss it thing. There's a reason for spinning it. It's not just showmanship. It's showmanship too. It's pretty cool to watch them do that. But there's a different reason. Do you ever take a turn a little too fast in your car? Shame on you.
Carson definitely does.
Now, but what happens to everything that's not nailed down?
Goes to the side.
It goes to the side, and specifically the outside of the curve, right?
They try and get.
When they're spinning, it's actually a fictional force, but it really feels like there's a force on you. People call it centrifugal force, like the word centrifuge. You get thrown to the outside, okay? So when you're spinning that pizza, it gets thrown to the outside. Long story short, it has the effect of widening and flattening the dough. Okay? Well, with that in mind, the Earth's spinning. That same centrifugal effect should act on the Earth. And so as the Earth spins, it should broaden and flatten. Now, it works well with pizza dough because pizza dough is kind of stretchy. There's some give to it. Okay. It's solid, but it's not rigidly solid, right? And so the pizza dough can change its shape. The earth is rigidly solid. Mr. Purdy, check these oceans. Well, you're not wrong. And the oceans bulge out a little bit more for that reason, but mainly because of tidal effects of the moon. Okay? But way back in the day, that brings me to the thought. I'll ask you something in a little bit. Way back in the day, Earth wasn't rigidly solid. I don't want to get into the whole how the Earth got here, biblical account versus science and all that good stuff. You decide what you believe for yourself, okay? But this does not necessarily contradict the Bible. Way back in the day, however it started, scientists hypothesized the Earth was liquid because of the interactions of the matter, the forces involved. So if you have a liquid Earth and it's spinning, it will flatten some. So long story short, and this diagram is going to be greatly exaggerated, but if you measure the polar diameter, or take half of it, the radius, and you compare it to the equatorial diameter, you get different numbers. Okay, Earth is flattened out. Now, and the same logic would apply to all the planets. Okay. Saturn is visibly oblate. If you see pictures, good pictures from telescopes of Saturn, you can see that it's not perfectly round, it's flattened. Boy, we're off subject big time, but that's okay. Nice physics discussion. Now, I got myself sidetracked. Let me float an idea past you. I'm thinking about doing this. This could be fun if we took it in the spirit in which it's intended and don't get hurtful. All right? Because this has the potential to hurt Mr. Bernichek's feelings badly. But talking with a freshman the other day, I made the observation, I forget what particular thing it was, but that I am older than such and such. It could be a fun little activity. I'm thinking about doing this. Have students come up with things and maybe have two different lists. Things that are Mr. Pernichek is older than, and things that are older than Mr. Pernichek. Let me give you an example. Mr. Pernichek is older than DVDs. They didn't exist when I was a kid. Okay? I am younger than rocks. Rocks predate me a little bit. Okay? But you can get, I made this observation with Edda was having a snack after school yesterday, and she was enjoying Doritos. I am older than Doritos. I remember when they first came out. Okay? You had one flavor choice. Corn. It was corn chips with salt. That was what Doritos were originally. Okay? And then when they came up with flavors, the first flavor was taco. But anyway, I think it could be kind of fun. What's older than Mr. Pernichek, or, you might be surprised both ways. I need to look it up, I'm not sure, but I believe that I am older than Reese's peanut butter cups. Pretty sure. Anyway, so, we might make that an assignment, each class come up with one or two things once a week. But
What year were you born?
so yeah, just to put a fine line on the thing, I am older than mankind landing on the moon. But I'm not as old as the first artificial satellite. Okay, so I'm kind of right in between there. I was born in September of 1961.
Dang it.
What?
Well, Mr. Brunichek is indeed younger than the first modern computer.
By how much? Well, the ENIAC goes back to like the 40s, I think.
Yeah, 45.
Not
He's
that
not-
old, dude.
I know. Well, I knew that.
Freddy's not in his 80s.
Well, to be fair, my grandpa was born in the 40s.
Look this up for me, just because.
Alright.
Pocket calculator. I think I may predate them.
I know how to program a calculator.
72.
Yeah, so I'm older than calculators.
72 You got 72? I got 67.
Either way,
Yeah.
I'm older than calculators. Now, I want to do a little bit of stuff today, but also we may very well end up early, or I got a few videos I want to show you as well, depending on how our time goes. But so the first thing here, we were on this slide yesterday. I want to point out something that I did not do a good job of what? See, you got too amused by this challenge now, didn't you? What am I older than?
Sticky notes.
Oh yeah. I'm older than Post-its.
Yeah.
Those came out in like 74-ish.
Well done.
Okay. And I happen to know that because I can tell you who invented it.
Are you older than cassettes?
I don't know, am I? I've got to think about I think I'm older than when they became popular.
62.
Okay, I'm older, and that actually makes me feel a little old, but I am older than cassette tapes. All right, so yeah, this could be fun.
The Rubik's
Take-
Cube.
Oh, definitely, that was a '70s thing.
Oh, yeah.
All right. Now, anyway, let's focus back on the chemistry for a little bit, shall we? I am not older than a mercurial barometer. All right? Evangelista Torricelli was running around, I don't know, you could look it up. I want to say 1600s, might be 7, I don't know. The video I'm going to show you might explain that. I forgot to mention this yesterday. Fill up a tube, invert it, dunk it in the tub. Some mercury will run out, but not all. Well, so what's in the space up here? Nothing. It is a vacuum. Vacuum is nothing. Okay. Is it a perfect vacuum? Well, it depends on the liquid you use, which is another reason that Torricelli picked mercury. Oops, doesn't write well if you don't set it for writing. Mercury is not very volatile. And that helps with this. What's volatile mean?
Ooh.
No. Although
Smell.
most people use it for that.
Smell. It
It
doesn't
means
evaporate.
it doesn't evaporate easily.
Yes.
Okay? So if you did this with water, water would evaporate, and so pretty soon you'd have water vapor in this part, right? And it would throw off your measurements. Okay? So if you have vapor particles up there, it does throw off your measurements, and you have to introduce a correction factor. So if you're doing really precise work with this, you can't just measure the height there. There is a temperature correction, there's a, but I'm not gonna drag you through all this. For our purposes, you measure the height difference between the top of the mercury pool and where it is in the tube. Now, just a little bit of Sandy Creek history. Way back once upon a time, we had one. Okay, sorta, but not in my working tenure. It got accidentally broken.
Oh.
All right.
Oh.
Now, not because this thing is 760 millimeters tall. Okay? Minimum. And you put a little bit extra because some days it's taller than that. So 760 millimeters. Oh, there. I mean, it's fairly tall. It came in a wooden cabinet to protect it, so a little bit taller. So the cabinet was actually about a meter tall. But the tube itself wasn't much bigger diameter than this marking utensil. You know, about as big around as my lovely 4-color pen. All right? So it's long and narrow. This pool here, heck, it could be the size of a swimming pool, but that's really wasteful. All it needs to be is big enough to dunk this tube in. So it was only about as big as the interior diameter was about a 50-cent piece. Okay, maybe just a touch bigger. So the cabinet was like a yard tall or meter tall, but only about 4 inches deep and only about 6 inches wide. So very long and narrow. Well, fragile. So normally you put it on a wall. It just, you know, mounting screws, and you screwed it to a wall or cabinet or something, right? But the summer before I came here, the janitors decided it'd be nice, paint the room for the new guy, you know, fresh coat of paint on the walls. And so they took off the equipment, and they're going, this thing looks kind of fragile. I don't want to break it. So they laid it down, which broke it, because this pool has to be open to the atmosphere. It looked solid, it had a lid on it, but just like, you know, if you're drinking out of a Yeti or whatever, there's a hole to let the air in, you know, right? It had a hole to let the air in to push on the pull of mercury. So when they laid it down, the mercury leaked out. I mean, it had to, gravity, it works, right? Oops. So they thought they were doing a good thing, okay? And they weren't doing a good thing. And just because of the geometry of it and how small it was and stuff, I tried to fix it, and I'm not coordinated enough, skilled enough, whatever, to fix it. Oops. Okay. I was watching a video. They said they don't make them or allow the sales of them in Europe ever since like 2009 because mercury's kind of toxic, right? So anyway, let's clean that off. 760. Okay, that's one of the important numbers that you need to know. Standard atmosphere. One way you can measure atmosphere or atmospheric pressure is just say, hey, we're under an atmosphere. 1 atmosphere. 1.00 atmospheres. But that depends on where you are, if you think about it. Okay, so if I'm on the earth and there's a mountain, the top of the atmosphere is kind of a hard thing to nail down. There's not a sharp line, it just kind of gradually fades into space. But I mean, if you think about it, if you're under an atmosphere, well, why didn't that work? There we go. It's not going to be as much pressure at the top of a mountain, right? So you're under an atmosphere where 1 atmosphere is defined as at sea level. But the problem with that is, what day is it? It depends on weather changes. One of the things that changes as a result of weather is atmospheric pressure. Sometimes air comes in and visits its friend. Let's get a little thicker here. Sometimes it goes away.
So what's the SI
Okay.
unit for measuring pressure?
I'm glad you asked. I'm gonna ignore you.
Okay.
Okay? But I'm glad you asked. It means you're working on stuff. So, 1 atmosphere, normal at sea pressure, average day is 760 millimeters of mercury. Now, are you under 1 atmosphere of pressure?
No.
Normally not. Why?
Because
We ain't at sea level. We're like 1,600 and some odd feet above sea level. Okay? And by the way, which sea level? Depends where you measure it. The Atlantic and the Pacific are not at the same level. So, I mean, defining some of these things, it's tough. Pressure gauges are used to measure the pressure within a contained unit of gas, such as an inflated tire.
PSI.
You may have done that. And that kind of tells you how pressure works. It's PSI, and it really ought to be PPSI. Pounds
per square.
per means divided by square inch. Pounds measures what? When you're measuring in pounds, what are you measuring?
Weight.
Which is the measure of the force of gravity. So pressure is force per square inches. It measures what? Math class, come on. Square anything is what? Square inches, square centimeters. You're talking about area. So pressure is force divided by area. Okay? Now, so it could be pounds per square inch, or we could be doing it in SI. But it would still be force per unit area. So the SI unit is a Pascal. But what the heck is a Pascal? Well, I'm glad you asked. A pressure of 1 Pascal is a force of 1 Newton exerted on an area of 1 square meter. Now, how much is a Newton? It's force, it's weight, right? It's almost exactly the weight of $1 worth of nickels. Okay? If you go to the bank and you get a roll of nickels, they put $1 in there, right? It's 100 grams. 100 grams is almost exactly 100 or 1 Newton. Okay, here on Earth, mass is technically not weight, although a lot of people call it like it is. Newtons is weight. Okay, so a roll of nickels over a meter squared. Now, just to give you a visual, how much is that? Why does it go to that keyboard automatically? I did some measuring yesterday. I thought we'd get to it yesterday. Silly me. And then I wrote all over it. So let me do some erasing. Yesterday, the eraser thing was bigger. I got no idea why, but it was. Okay, now you see I left a red mark at the bottom. Oops, I'm gonna leave that there. And I left a red mark at the top. And for some, I can't move this or make it disappear, I don't think so. But anyway, the red mark's behind there. The board's not quite a meter tall. It's like 70 some centimeters. But so I measured, you know, the width of the board and the height of the board, and I did my math. This area bounded by those two red lines is a square meter. Okay? So if I laid it on the floor and I put a Newton on it, a Newton is, Jack Clark likes to play with this, which is how come the cord's all tangled and stuff now. Alright? But this thing says it weighs a Newton. And it's really pretty darn close. 100 grams. Okay? Pass it around if you want to experience a Newton. Same as the weight of a roll of nickels, right? Now, how many of those apples would stack on that area to equal the weight of the column of air that would be on there? If you laid that on the floor, magic saw, first of all, you air freeze. No random motions, you shut off all the wind. Magic saw. Clean up to the top of the atmosphere. Catch all the air molecules over that thing and only over that thing and weigh them up. How much you got? 101,300. Newtons of weight would be on this 1 square meter at sea level on an average day. That's a lot of them. And by the way, it's not just down. The air doesn't just push down. It pushes sideways. So it's pushing that hard sideways. It's pushing that hard actually on the bottom of the lab tables. The air pushes up too. It pushes in every direction. The pressure at sea level, average day, that much. Technically, that's the SI label, only instead of saying this, we say pascals. But, since that is such a big number, sometimes instead of using pascals, abbreviated capital P lowercase a, by the way, instead of measuring in pascals, sometimes we measure in kilopascals. What would that do to the number?
Shrink it by 1,000, or divide it by 1,000.
101.3. Okay? Now, just because, those of you that are in Quiz Bowl, listen up. Now, the rest of you can just kind of block this out, or you can pay attention and learn a little extra something. Atmospheric pressure is 1013 millibars. That came up at the Quiz Bowl in Nelson.
Oh, it did.
Okay. Do you see where a millibar might come from? A millibar is
A millipascal.
what? Yeah. Okay. So if you divide that by 1,000, right? It's related to pascals and kilopascals, right?
Yeah.
All right. What am I gonna do? I'm gonna go back to this.
So 101.3 kPAs
Is
equivalent to 760
millimeters
of
is 1 atmosphere.
Gotcha.
And there's a fourth one that we use. And it is
PSI.
no, yeah, 14.7 PSI.
TSPI.
14.7 PSI. Now, so this list, table 11.1 in your book, memorize it, okay? You will need it to be successful on the test, and I'm not gonna provide you the numbers. That's only 4 numbers, that's not that hard. Memorize those, okay? And one of them's really easy, 1. Don't just memorize the numbers, know the labels that go with them, okay?
So, like, for example, on our worksheet, it's giving us, like, convert this number into ATMs, and it's like 785.2 millimeters of HG. The number comes out to be like 1.033155789.
Which sounds about right. It should be a little bit more than 1.
Yeah. You want us,
Okay.
how far do you want us to go?
That's a good question. I'm gonna ignore you again.
Okay.
You asking a lot of, see, you got me in trouble. When I listened to you yesterday, I lost sleep. So, Not listening to you anymore.
Oh.
No.
That's not very nice.
All right, to find the absolute pressure at, oh, look at this. I shut off my underliner and I shouldn't have. There's a couple of kinds of pressure. Might or might not be a test question. Wink, wink, nod, nod. There's absolute pressure and there's gauge pressure. Absolute pressure is the total pressure. Gauge pressure is what the gauge says. Aren't those two things the same? Nope. Let's say Mr. Pernichek decides to be a vandal, so I go out to the parking lot and I remove the valve stem cover from your vehicle's tire, and then I push on the little thing in the middle of the stem, and I start to hear as the air leaves your tire. And I keep pushing that thing until I stop hearing. So in other words, you have a flat tire, right? Literally, it's sitting on the rim in the parking lot, okay? Is there air in the tire?
Yes.
Yeah. What's the gauge gonna say
Zero.
when you slap it on? It's gonna say 0, but you just told me there's air in the tire. If there's air pressure. So how come the gauge says 0?
Because because there's atmospheric pressure.
Because machine got
The gauge, most gauges, you could set it to read correctly, but most gauges read this. It's above and beyond. Atmospheric. Your tire gauge pressure isn't telling you the pressure in the tire. It's telling you how much it is more than what normal atmospheric pressure is. Okay? Anybody know what your tire gauge pressure should be?
32, 35,
Ish,
34.
32, 35, depends on the tire.
Semis go up to like 100.
There's a little tag in the, like, you open the door and you look at the frame by the driver's door. There's a little tag tells you what it should say. Okay? Some tires, a lot of tires, kind of hard to read them because it's like black on black, but you read, they have printed the maximum tire pressure, okay? Now, not to pick on young ladies, but this story, when I was first told it, happened to involve a young lady. Sometimes people go, my dad takes care of that for me. My daughter does, still, all right? So, girl's going off to college. Dad isn't right there at the moment. So she pulls into the service station to fill her tank with gas because apparently Dad taught her how to do that. Okay? While she's gassing up the car, she noticed that the tires, they're not perfectly round. A little flat on the bottom. Going, my tire's getting low. I better air it up. Some gas stations, they have the air thing right there, a machine right by, so that you can air up your tire while you're filling with gas, right? So she's filling the thing with air. Another guy, somebody else's dad, pulls up, watching her doing this for a while, and starts to get bothered and says, Miss, what are you doing? And she's, I'm airing up my tire, it's flat. And he says, how you gonna know when you're done? And she says, when it's round. And he says, no, let me show you something. This thing's called a tire pressure gauge. Okay? Let's check how much air you have in your tire.
It's like 43 or something.
She was up to about 70 something.
Oh my god.
Okay?
How'd that not?
Explode?
Yeah.
Luck.
That could have killed her, right?
Yes. Yes. So, please and thank you. A modern steel belted radial tire looks a little flat when it is properly inflated. Okay? Please be careful. So, if you want the total pressure, the absolute pressure when you're using the tire gauge, you take what the gauge reads and you add standard pressure, 14.7 psi. If you're using the KPA side, you take what the gauge says and you add 101.3. Okay? That's easy peasy. We're done. All right. I bogged down a little more than I intended to. My apologies. I do want to show you a few things here. This is the first thing I want to show you, I think. Well, that's not it. Where the heck did that come from? Chrome. There you go. So let's shut off that one. I got no idea why that one's there. I want this one. TED Talks are usually pretty good and fairly reliable. Let's listen to the TED Talk.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could
10 point what? 3. That's about 34 feet, which is the number I told you about yesterday, I think. Now, the well for your irrigation system might be deeper than that. Modern pumps, they work a little bit differently than the old Italian, and they can take water higher than what those old pumps could do. But the old pumps depended on atmospheric pressure to make the darn thing work, and the most you could get is how high could water or could air hold it up, which was only 34 feet above the water table, right? Which, amazingly enough, is this: if we got a super long straw and put it over the landing there into the cup on the floor down there, would you be able to suction up and get a drink from that cup down there? Actually, yeah,
Well,
probably. You might have a bigger of a headache when you were done, okay? But the most that you're ever going to be able to suck something up a straw is 10 meters, 10.3, right? Because straws work on atmospheric pressure. You don't suck the material up the straw. You remove the air from the straw. The surrounding air pushes the liquid up the straw for you.
lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no
From
air having
here
entered the
to
tube,
there.
Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of
puts him in
focusing
the
on the empty space
1600s.
inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall.
Again,
Not only did
rounding.
this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube
That's
taken up a
by
mountain
Pascal.
and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure
Does the
until
pressure
2007,
decrease
when
without-
restrictions on the use of mercury due to its toxicity led to them
Noah,
Why does the pressure decrease with the higher altitude?
think about it. You're measuring how much air is pushing down on you.
And
Right,
when
with
you're-
less air. Yeah, just making sure.
Less air pressure.
no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Now, if you go to an old doctor in an old doctor's office, some of them, their blood pressure cuff is like bolted to the wall. And if you look real careful, the tube in there, it's got mercury in it. The old ones do. Okay?
Old
By the way, what's the fancy name for the blood pressure cuff?
Pressure gauge.
Oh no, on hugger.
It's a
hugger.
sphygmomanometer.
A sphygmomanometer.
Sphygmomanometer. It's one of your worksheet
That's
questions.
that's a fun word.
A manometer is a pressure gauge.
Do you know what else is a fun
Oh.
word? Heptatonic.
I'll take your word on that one.
What's your heptatonic?
It's a 100-sided shape.
Yeah, everybody knows that.
Yeah.
Duh.
We learned this
Okay.
in elementary.
I probably need to shut off the recording. You're still being recorded.